Uh, Good morning, everyone. I want to apologize in advance for my handwriting. I think it will improve as we progress through the presentation, as I regain my calligraphic abilities. So today, I would like to talk about something that you all use, either explicitly or implicitly, or many of us use in our work. It's Schur transform, and I would like to think about classical and quantum features of Schur transforms. So this is a joint work with a collaborator of mine. He's a PhD student at Oxford, Sergii, and that's the preprint over here. So the plan is the following. We'll just have a gentle introduction to what a Schur transform is. Then we'll have a quick look at very biased selection of applications, and then discuss about implementation of Schur transform, and then we'll move to the second part of my talk, which is about properties of Schur transform, studied through the computational lens. In particular, something that's what we call permutational quantum computing, and we'll conclude with some open questions. So, to start, let's think about a description of a qubit. Let's remember what we studied in first year physics, how we can write an orthonormal basis of a qubit. In this physicsy way, we have Jm numbers here, and we can write the qubit in this basis here, where J jumps to half spins. So you have like 0, half, 1, 3 over 2, 2 over 5 over 2, and so on. For those who don't like thinking about this type of basis, in terms of this type of basis, they can always think about computational basis and the equivalent mapping. 0 maps to half minus a half, 1 maps to a half and a half. And what we would like to understand, having two separate descriptions of systems, system 1 and system 2, how to write a system in joint, so-called coupled basis. So physicists have solved this question a long time ago. We have two systems here in an uncoupled basis. It's a tensor product basis here, and we can devise what's called a coupled basis here. It's a basis of states that comprises of states that have the following structure. Now J's range from the sum of J1 plus J2 and all the way to their absolute value of their difference. And M, the multiplicity, goes from J to minus J. Well, now this J is over here. So this transformation from a coupled basis to an uncoupled basis is a well-known Clebsch-Gordon transform. It works as follows. So for every state, you can actually, it's a very simple exercise. You can write it down for two qubits. A coupled basis of two qubits here, each of them having basis J1 M1, written using basis vectors J1 M1 and J2 M2, can be written with the help of this relation, and this is obviously the well-known Clebsch-Gordon coefficients. So the matrix that takes you from here to here is a matrix which has, it's a unitary linear transformation that has Cj coefficients in various places. So how does it relate to Schur transform? Well, a sequence of Clebsch-Gordon coefficients. Imagine you have an n particles and you want to have a coupled basis of n particles. And what you do, you can start with the first two qubits and some auxiliary register and apply the Clebsch-Gordon transform, and then you do it again at another qubit and another and another. You have this chain of Clebsch-Gordon transforms, and at the end, what you get, the total transformation here is called the Schur transform. So these p's here that you get as a side product here, they simply correspond to encoding in the Young orthogonal basis the value of p, what is the permutational, that corresponds to a permutational symmetry of a state. Alternatively, kind of more mathematically, you can think about a Schur transform as doing the following easily recognizable partition of a space of state space of n qubits, qdits, into a particular direct sum of subspaces, where lambda now ranges over all set of possible partitions of n into less than d parts. So Schur transform maps the basis state. Essentially, it gives you a mapping from computational tensor product computational basis states to a one unified state which has the following form here. It's just the same, slightly more rigorous definition of what a Schur transform is. So where do we use Schur transform? Well, there are quite a few applications. I thought I'd pick some of the lesser knowns, hopefully. And one of them is about, some of you probably know it, is about communication without a shared reference frame. Imagine you have two parties, Alice and Bob, and Alice wants to communicate to Bob a classical bit. What they have a quantum channel, and so like she can send qubits to Bob, but the measurement apparatus, they're completely desynchronized, so they cannot really, when Alice, let's say Alice sends state 0, Bob may measure plus or something else. There's no way, imagine for a moment, there's no way for them to synchronize these measurement devices. So the question is, can sending a single qubit help them communicate? Help them send, can Alice send 0 or 1 classical bit using a single qubit to Bob reliably, perfectly? And the answer is no, as it turns out. But when Alice is allowed to do send 2 qubits, she can do it. The actual protocol is pretty simple. So imagine if Alice wants to communicate B0, Alice wants to communicate bit B. When B equals to 0, Alice sends a singlet. When B equals 1, she sends one of the triplet states, one of the other states, any state in the symmetric subspace. And so what Bob does, Bob measures two projectors, symmetric and anti-symmetric subspace. When it gets, when this detector clicks, you get 0 or 1. To send, you can actually generalize this, and you can send, if you have a number of qubits, if you have a whole, you ask yourself a question, what's the best possible rate you can achieve in this kind of way? And the answer is, you can actually, first, Alice can having n qubits, she can apply a Schur transform in a sequential way, coupling them, as I showed in a circuit before. And then she can send more information. How much more information? Well, as she can send as many bits as the number of different EREPs that occur in this decomposition. So here, parties only have to agree on one thing. Parties only have to agree on how they label the qubits. Where's qubit 1, 2, 3, and 4? And this can be agreed, you can just simply rank them, and this has nothing to do with the reference frame. This is just a number. They just pre-agree on the labeling of each qubit. So that's, for this type of protocol, you really need to apply a Schur transform. And notice that this is year 2003, and the first efficient quantum circuit for Schur transform appeared only a few years later. So until 2005, much to my surprise, it wasn't clear that there was even a quantum circuit that would perform a Schur transform. Well, we'll talk about this shortly after. Another application where Schur transform is crucial is the following. This was done in Kiribella and co-authors a few years ago. So imagine Alice has a quantum state rho tensor n, and Bob has a unitary. Bob has a quantum computer. Bob wants to apply, Alice wants Bob's unitary applied to her state, and she wants it to be returned to her. So they have a quantum channel, and the goal is to minimize the amount of information, quantum information, that Alice sends to Bob in this scenario. So naively, you would think, well, I just have to send n qubits, or qubits, whatever the underlying dimension here is, to Bob in order to get this. So you send n qubits to Bob, Bob applies transformation, and you send n qubits back. But it turns out that you can do much better, of course, by leveraging the structure of the states. what you can do, Alice can apply, can encode her state into this kind of in a Schur basis, so she can apply the Schur transform, and she will have this decomposition of labels and multiplicities. And similarly, Bob can turn his unitary into two parts. He can partition a unitary in a way where this, into two parts essentially. The first part is acting on a label, and the other part is acting on the multiplicity space. So what Alice would do, Alice would repackage her system and send only the labels. They do have to know exactly how many particles, Bob has to know how many particles are in the game though. And then Bob applies this part of unitary to the label space and returns it, essentially achieving a label space, as you know, is exponentially smaller space compared to multiplicity space. So we get exponential gains in communication, exponential savings in communication rates. Another example that also was studied in this paper by Kiribella was about gate replication. As we know, you cannot clone quantum states reliably. This is not true for quantum for unitaries. If you have, say, a unitary, if you have n uses of unitary, you can simulate up to m uses of unitary, where m is at most n squared. And this again is done by using Schur transform. But I won't stop here. For those who are interested, really check out this paper. It's really, really simple and very, very interesting. So further afield, there are, again, this is just a very small selection of applications where Schur transform plays a role. So one of them, a lot of papers actually are various permutations of Matsumoto and Hayashi authors. So one of them is universal distortion-free entanglement concentration. Then papers that talk about universal compression of quantum information. And then there's a bulk of work, a whole body of work actually, on encoding and decoding into these distortion-free subspaces. And also estimating spectrum of density operators by Kyle and Werner. Again, long before we actually knew that Schur transform could be efficiently implemented on a quantum computer. I should point that universal compression of quantum information, this type of ideas, were first brought up implicitly featured. They didn't connect, these ideas were featured in a paper by Richard Jozsa and Horodetsky brothers, the trio of them. They were doing essentially universal compression of quantum information, but without perhaps explicitly mentioning the Schur transform. And then later on, these guys picked up on that. So this is just a very small subset of applications where Schur transform plays a role. So what we were motivated by studying the Schur transform from this computational perspective. Is it really a quantum transform, or perhaps there are some classical bits it can be perhaps simulated classically. So before I move to the second part of my talk, I would like to comment on a recent very active development on the sort of a circuit synthesis frontier for Schur transforms. So the first circuit was given by Bacon, Harrow, and Chung in 2005. It has this rather obscure runtime, so it's polynomially a number of particles, local dimension, and it's scales like log 1 over epsilon in terms of error. But this circuit, they weren't really optimizing for a particularly good gate set. Very recently, Kirby and Strelchuk, they found efficient Clifford plus T circuits where for qubits the runtime goes as n to the 4 log n over epsilon, but for qdits the kind of the runtime is pretty dismal. It goes as n to the d. Essentially, this factor quickly dominates everything. So things are really these circuits don't look very efficient so far. And just recently in April, Harry Crowby from Raytheon, he found a new way of synthesizing the Schur transform that is logarithmic in the dimension. So this is very much an active area. People try to understand how to implement this type of transformations. And so we were thinking about a Schur transform, but we stumbled on it in a rather incidental way with my collaborator when we were thinking about what's called the permutational quantum computing. So permutational quantum computing is a particular model of computation which was inspired by the spin framework, the kind of ideas from spin framework type of constructions by Roger Penrose. He had this paper about, it's called Angular Momentum, in 1971, an approach to combinatorial space-time. And then building on these ideas, Marzolli and Rossetti in 2005, and later Jordan in 2009, defined a rigorous model of computation, which then became the permutational quantum computing. You can regard this model as so-called topological quantum computing light. So, so it was meant to be a kind of a stripped-down version of TQC, where instead of thinking of particle trajectories or directionality during the computation, we replace them with simple permutations. And as a result, we end up having a much simpler model that we can think about, and we would and simpler not only compared to TQC, but pretty much simpler than any other universal model of computation. And also PQC was conjectured to capture a lot of non-trivial aspects of quantum computation. In fact, Steve Jordan in 2009 conjectured that it may be a class, a subclass within a BQP, that it was clear, well, there was strong evidence that it may not be within fully, it may not capture everything in BQP, but it can be strongly, it could be bigger than BQP. So naturally, we were drawn to this type of model because we wanted to understand quantum supremacy, quantum advantage, all these kind of questions. Well, we didn't know. The bottom line is that we didn't know what's the real power of this model. So let me describe you what permutational quantum computing does. Let's throw in a few definitions. So let's label our qubits from 0 to n minus 1. Then we define the spin of kth qubit as this triple here. And then the total spin of a subset of qubits is naturally defined as just the square of the sum, where k now is within this given subset A. And we also need a spin projection operator along the z-axis, which will be given by this quantity here. And PQC essentially works in a basis defined by a complete set of commuting operators of this kind. Well, when you look at them, it will strike you that for arbitrary subsets here, these operators need not commute necessarily. But we will pick our basis in a way, we'll pick these operators in a way that they will be commuting. And when does this happen? Well, a sufficient condition for commutation is for two operators to commute is when A intersection of A and B is empty, or the indices in A, they're all fully contained in subset B. So how do we get this? How do we generate these operators, which will further define our permutational quantum computing? So let's start with spin half particles. Let's label them. We have 3 of them. And what we'll do, we'll first look at the operator, total spin operator of the first 2 guys. And then for the first 3 guys. So as you see, 0, 1 is within the subset 0, 1, 2. So that's good. These guys commute. And then we add, at the very end here, the very root of the tree, we add another operator here, z, on all of them, which would be this projection on the axis z. So this for those who know a few things about topological quantum computing, they may recognize these coupling diagrams, they look very similar to fusion trees in TQC. So what would be the basis of this model? So what basis this PQC is operating in? So having this little picture here, it corresponds to a set of basis states, J012, M012, and J01. It's a kind of a Schur transform. You start with the computational basis states here. You perform a particular transformation, well, Schur transform, as you would have guessed already, and you get a state here. And this type of states can be indeed efficiently prepared using the Schur transform, as we've seen before, using any kind of circuits that's been designed to implement the Schur transform. So permutational quantum computing essentially is a 3-step process. In the first step, we perform the Schur transform. Then we run a program on this machine. The program is actually a simple set of permutations. So we permute the labels of the underlying states here. And then we perform the inverse Schur transform to get state y. And we measure this state we measure these labels and get classical results. It's very simple, very tractable model, and there is nothing extra than a bunch of Schur transforms and permutations in between. So the strength of this model is attributable to the power or the properties of the Schur transform. So why PQC is actually, why people care about it? It's pretty strange model to think about. So first of all, it does resemble topological quantum computing without added difficulties of directionality. And another thing which was remarked by Stephen Jordan was that the amplitudes of PQC processes, they correspond to matrix elements of some irrap matrices of symmetric group on n elements. I can give you the more rigorous definition of this correspondence at the end of my talk. And what was curious was that there was no known efficient classical algorithms to approximate these matrix elements, which led people like Stephen Jordan to conclude that the power of PQC in general is better, or PQC is more powerful than your ordinary classical computer. And so the interesting thing is that to characterize the power of PQC, you only have to think about quantum Schur transforms. As I already mentioned, people were interested in PQC from the point of view of trying to develop some kind of supremacy type proposals. Another rather striking thing is that PQC, permutational quantum computers, can simulate processes in what's called the Ponzano-Regge spin-foam models of quantum gravity. And in polytime. Both of these can be done in polytime on a PQC machine. So what we were doing, we spent a long time trying to get some quantum advantage out of this circuits, but we failed, so we turned the other way, and we found that the permutational quantum computing processes turn out to be efficiently classically simulatable. So everything that a PQC machine can do, you can do in polytime on a classical computer. And the way we proceed is not very complicated. We do it by showing that everything that PQC, any state that occurs within the PQC machine is a computationally tractable state. So what is computational tractable states? So this is a definition, this was formalized by Van den Est in 2009. So an n-qubit state psi is computationally tractable when the two conditions hold. The overlaps can be computed efficiently for any computational basis state y. And second condition, it is possible to draw samples from for any y from this particular distribution on a classical computer efficiently. So if we prove that any state that arises from PQC, the function of PQC, fulfills two of these conditions, then we will prove the simulation result in a strong sense. One thing that really strikes you is that whenever you think about Schur transforms, you implicitly have a very powerful tool, which is the conservation of angular momentum. If you have a fixed number of particles, you have the conservation of angular momentum here. So if this is for two particles, you have but only particular Clebsch-Gordon coefficients arising. So in the computational basis, you can think of the Schur transform state. Let's say M0 and 1 and M2 are the computational basis states. Then you represent your Schur transform state from this using a sequence of sums, this kind of sums over all m's of Clebsch-Gordon coefficients. And we can get rid of a lot of terms in the sums. Normally, in general, the sums are exponentially big, but in m, a number of m's. But conservation of angular momentum allows us to really keep this number of different amplitudes, at bay. They don't blow up exponentially, as we'll see shortly. So let's try and prove this first part here. So as I mentioned, we can represent any state using this type of expression. And let's start with a small example. So we have a 4-partite computational basis state, and let's try to understand how do these overlaps look. So if you just compute this, what you get that because of the conservation of angular momentum, all the intermediate terms in the sum will vanish, and these overlaps will be nothing but the product of n-1 Clebsch-Gordon coefficients. And don't forget that we are talking qubits here, so Clebsch-Gordon coefficients are efficiently, they have closed formula, in fact. So we can approximate them, we can compute them directly using all kinds of algorithms that are out there. So yeah, it turns out that the complexity of this part is nothing else but computing n-1 terms, which, as I said, can be done with exponential accuracy. So we tick off the first part, and for the second property, we would like to understand just how difficult it is to draw samples from a distribution on the classical computer here. What if we measure? Can we actually say something about the distribution? Can we characterize it classically or not? Notice we don't have any features like concentration. It's just a generic distribution that arises from application of Schur circuits. So let's define our probability distribution for some bit string y. And we remember that, well, we can use this simple marginal rule. The probability of yk n-1 is just summed up probabilities sums over y0 to yk minus 1 of these marginals here. So let's try to understand how can we decompose this probability distribution. So in full generality, this probability distribution is this horrible exponentially big sum of Clebsch-Gordons, squares of Clebsch-Gordon coefficients, summed over all m's from m0 to mk minus 1, mn minus 1, sorry. But then what you notice, again, due to conservation of angular momentum, is that you can pull out a single surviving coefficient in front of the sum of n-2 terms here. So your support here shrunk by 1, and all you have to do to update the distribution is to multiply it by a particular Clebsch-Gordon coefficient, again, which is efficiently computable. Then to generate this type of distribution, all you need to do this kind of iterative process where you start with y n-1, and then you keep on building the distribution up, every time multiplying by the respective Clebsch-Gordon coefficient. So again, this is just n-1 steps, and it boils down to computing products of only n-1 Clebsch-Gordon coefficients as opposed to exponential sum of those. Lastly, what we need is the lemma that talks about two computations. So now we've established that we have everything that's happening in here after this gate and after this gate is computationally tractable. So what we would like to know that computing overlaps of two computationally tractable states is still efficient, because states could be computationally tractable for different reasons, and we would like to know whether there is an algorithm that computes these inner products efficiently, these overlaps efficiently. And again, Van den Nest gives a prescription of how to do this, and there is an algorithm that's this polynomial in epsilon and delta that computes these overlaps efficiently. So then, coming back to PQC, for any program u pi, which is here, we can efficiently approximate this distribution here, p pi y given x, because this state is computationally tractable. Then after we apply the Schur transform, this state becomes computationally tractable, and permutations here just permute the labels without affecting the computational tractability. And we can compute this term again efficiently. So what have we learned about PQC? So we learned that states of this kind are computationally tractable. States that arise in PQC are computationally tractable for any program, and overlaps can be computed with exponential precision in poly time. Notice that we do need exponential precision if we want to maintain the right kind of simulation result, as opposed to just polynomial. And this type of proof covers all processes within permutational quantum computing. And moreover, the proof techniques work for not only for this permutational type programs, but for any unitaries that are sandwiched between the Schur transform that are diagonal in Z basis, for which entries are efficiently classically computable. And we call this type of circuits Schur sampling circuits, in analogy to kind of Fourier, to quantum Fourier sampling. So that's kind of a short summary of where PQC is, and unlike our initial hope, it's no more quantum than it's a Clifford-based computation. So it's a fully classical model, and we also, as a bonus, we get several efficient algorithms to approximate matrix elements of some ERAPs, and we get efficient algorithms to compute transition amplitudes in various spin-foam kind of quantum gravity type settings. So what we would like to do next? So it turns out these Schur circuits, despite the fact that they're classically efficiently simulatable, they're really good randomizers. There's an overwhelming numerical evidence that these guys could be designs, K designs for some small k, K being 4, 5, 6 even. And this is really curious because if you contrast it to another well-known family of classically simulatable circuits, Cliffords tend to be 3 designs, but not 4 designs. And for some applications, you absolutely need 4 designs. So this Schur sampling circuits, they have the potential of being 4 designs and above, at least based on our numerical explorations. Another really unexpected open question is that it turns out this type of circuits are related to Boson sampling. Earlier this year, Peter Turner and Alexander Moylet, I forgot to write the reference there. They managed to formalize pretty much every Boson sampling experiment as a particular circuit here, where you do inverse Schur transform. This is important, not the straightforward, but the inverse Schur transform. Then you do some stuff in between, and then you do it again. So here, a lot of things can happen. So you can lose your particles, you can throw them away, or you can maybe introduce some noise models. And they want to understand Boson sampling experiments through this kind of framework, using this type of models. And as you see, they're really related to the permutational quantum computing, and somewhat too related maybe, because a large chunk of these models may actually turn out to be efficiently classically simulatable, which wouldn't be the very good news for supremacy guys. But nevertheless, they do something quite different to what we do, to what permutational computing does. They don't just permute things, they do more sophisticated things. But now that we know exactly what Schur transform does and what type of states arise before and after Schur transform, we are in a good position to study these error models and to study what's happening with all these experiments as nicely encoded in this model. So yeah, and this kind of brings me to another question. What other programs we can run on this permutational quantum machine and still remain kind of within classically sort of computationally tractable? And lastly, I would like to I would like to think about Schur transforms in analogy to Fourier transform and define it on groups. So far we only dealt with symmetric group, but there may be a way of thinking about this type of transformations which in addition bring some extra group structures. So that's all that I wanted to say. There is for those who are interested in the kind of questions that PQC can solve, you can ask me I have a little slide here telling you exactly what can be done efficiently now. So that's all.
Can you elaborate on the first question? That this might be K-design. Isn't angular momentum conserved under this Hamilton?
So I'm looking at how anti-concentrated are the output probabilities of Schur sampling circuits, and there is a way they look too. It averages things very well. I would say it just makes things very homogeneous, at least in my numerical experiments, which led me to believe that you can think about them as efficient randomizers.
I mean, it might be true that in each sector you randomize, but you can't mix the sectors.
So the point is that what you do in the middle here. This is what affects it. You have random permutations on labels, right? So if you remove the program, this is trivial, right? This identity. But what you do here, when you do things, when you fiddle with labels, you really entangle things, and then you do the inverse Schur transform. So you really kind of scramble things quite well inside if you apply these permutations.
Can I ask you about the next slide?
Yeah, sure. So the problem that can be efficiently solved now classically is the following. So as Stephen Jordan defined it, we have an approximate, the problem is to approximate matrix element in what's called a Young-Yamanouchi basis of an irrep of Sn. So the input, you are given a Young diagram, gamma with 2 rows specifying the irreps, a permutation from Sn, and a pair of standard Young tableaus of shape Y, indicating which element, matrix element we want. And epsilon, we want the accuracy epsilon. And what we would like to know, we would like to have I want the algorithm to output the specified matrix element to within plus minus epsilon. So in computational group theory, there was no known polytime algorithm to approximate these things for a given accuracy epsilon. And sort of through indirect route, by making PQC classical, we found this type of algorithm. So which brings another kind of set of questions. What other interesting problems of computational group theory can be cast as polytime algorithms, as polytime computations in PQC? Or maybe there should be not just permutation, but some other GQC, group quantum computing, where you have something other than Sn. Because a lot of techniques will carry over, actually.
I have one
Yeah.
question. So, have you thought about this with qubits?
Yeah, so things tend to break down fairly quickly with qubits, partly because the underlying. Okay, so there are two really important things here. One is the complexity of these guys. For qubits, they are not particularly nice. Clebsch-Gordon coefficients for SUDs are not the nicest thing to compute. And secondly, is it's very important how we choose this type of couplings, how we couple the bases. Because if you couple the bases in a strange way, then you lose all kinds of nice features, and things become not classically efficiently simulatable. So yeah, this is very important, like how you fuse things. So what we do here, see, we do sequentially. Particle 1 and 2, 1 and 3, and so on and so forth. So yeah.
You should also look at, there are modified fusion rules. If you go away from these classical groups, then they're a little bit more non-commutative.
Yeah, so...
that's sort of related, because if these coefficients then change...
That's right. There's a whole kind of geometrical complexity behind these things, because you all of a sudden replace Clebsch-Gordons with something else for which you can bring in all these conjectures.
Right.
And then you are back in your supremacy fairyland. So that's right. Yeah. So it's a very versatile model. Right.
no more questions, let's thank you again.